Hi, welcome back to Chapter 7. This is the second video in Chapter 7. And in this video, we're going to talk about no bounds checking in C++. So in no bounds checking in C++, what that means is when you create an array, you start by telling it how many spots or how many pieces of data can be in this array. And so far, we've been kind of using ints as our example of arrays. And when we do that, we say how many ints we set up how many ints we want in an actual array. Well, C++ does not stop you from trying to write data beyond the bounds of the array. Some of your languages that you use today, some of the more common languages like C Sharp, higher level languages like that, have bound checking, but C++ does not. So let's take this program right here, or the snippet of program right here, and look at this as an example. What we're going to do is we're going to set up an array that has 3 elements. But we're going to actually sit in a for loop 5 times and put 100 in each space. So 0 is going to have 100, 1 is going to have 100, 2, so forth and so on, all the way out to, well, actually it would be 4. It would have 100 in as well. So what does that look like then when that happens? Well, think of memory as parking spaces. And each space, let's say, is 4 bytes. When we set up an array of 3 ints, we've asked the system to allocate us 3 blocks next to each other. Again, the index is how we get to those 3 spots. So this is index 0, this is index 1, and index 2, just as we've said down here. When we're accessing them, remember that we take the address that is stored in the array's name values, and then we add whatever indexer is requested. So if we want space 0, let's say that the address for this, come on, pen. The address space for this is 0x123. That's just the memory location for that particular spot. If I want values 1, then I'm saying go to values where the address is and add 1 times the size of an int. And that is going to take us to the beginning of that spot. If I want the second value, then it's the same thing, except I'm going to look at the indexer. It's going to be 2, so it's going to be the address plus 2 times int, which brings us to that third spot. Well, because C++ doesn't have bounds checking, I can put 3 in here, and it's going to go and just blindly go to the beginning of that third spot. Same thing, same, so forth. We can continue. Let me clear that out. And, we can continue to add the address plus 4 or 5 or 6. And so in that code that we just had, where we wrote it 5 times, what we did get was exactly that. It wrote it here, then here, then here, and then it wrote it outside of our actual array. And now, hopefully, this memory wasn't being used. Maybe it was. Maybe it was being used by our program. Maybe another array is there, or maybe other variables are there. And we could cause corrupt data. Hopefully, this error would make our application crash and no harm, no foul. But again, if this space was set up as some other variable in our program, maybe we are a bank and we're adding values, and we meant to add later on in our program, we're going to add this value that happens to be stored here and this value that was stored here. But now that we've overwritten it with the wrong data, our results are going to be wrong. By the way, this is one of the most complicated things to debug because you're going to be looking in the code that has to do with adding this first, and it's going to look right. Everything's going to look perfect. And when in debug mode, because you're only testing that one piece, everything's going to work great. Then the next thing you're going to do is you're going to debug wherever the original position in the code that writes the data there, and you're going to find out that that all works fine. You're never going to suspect that somewhere you have a piece of rogue code that's overwriting this memory with junk. And so it's really difficult to debug these issues. Um, the next thing is this is one of the ways hackers use what's known as a buffer overrun to hack machines. So let's talk a little bit about that because it's pretty interesting on how that works. So again, this is just kind of one conversation about how this is done, and it is definitely at a very high level. Not getting too deep into the details, and I know that there's going to be a hacker among you that goes, "He's leaving out a lot," or he's kind of not saying it 100% correct. Again, this is just more for visual purposes to understand and why you want to avoid this because it can be a problem. So one way to use buffer overruns is a hacker will go to your code and he or she is going to look through your code looking for these buffer overruns because they know that if they do this, what they're looking for is imagine again your memory as this big box that's segmented as like a parking lot, right? And what they know is that your application is going to do all these steps. And part of these steps is to look at memory to get values. And then sometimes some of these steps we'll look at memory and go, oh, okay, that tells me I need to go back to this spot in the code, or maybe I need to call this piece of code. And so there's your code, right? Let's erase. Ugh, I did not want to do that. So it's a habit of doing that. So let's draw our memory box here again. So this is, by the way, I'm kind of showing you here a depicting a what a heap would look like. In case you're all curious and want to do more research, this was kind of typically known as a heap overrun. And so again, so we have our code, and at some point maybe it needs to look back for variables, and sometimes it tells us, oh, well, you actually need to go to this space in memory because that's where the next set of code is. So what can happen is there's two ways that a buffer overrun can help. One way is the hacker gets another piece of code, what's called the payload. So this is the payload, and they get this stored somewhere in memory. Let's say it's stored right there, and that's the start of it, I should say. Okay. Then they go to your application because everybody's using it, and they say, "Oh, here's this buffer overrun. This buffer overrun right here is going to do something to the memory that's going to take up these next spaces, but it shouldn't take up these next two spaces. And in fact, if I put something really cool in here, something worthwhile, like, hey, an instruction to go here and start running code, I can get my payload run." So maybe let's say that this is a login. This is an array of strings. An array of characters, and it should be only 8 characters. That's what I've gone with. But there's no checking, no bounds checking, so I can actually put as many characters as I want. And so in looking at everybody's code and looking at your code, I go, oh, if I use this particular piece in everything after those 8 chars, I can actually script as a code language, then maybe I can jump to this particular memory, which is exactly where I loaded my payload into. And by doing that, now I'm going to run my payload and I'm going to get whatever I want, including possibly admin rights to your computer. So that's one way of doing a buffer overrun. Again, the idea is the same for a lot of the buffer overruns. Is you have memory, you have a spot in memory that is meant to have a set of data entered, but you can see that you can easily manipulate the system using a buffer overrun to write information into concurrent memory spaces that are later used by something else. And again, so this is kind of what should be used, and then this is one of our injection points. We're going to inject something in here, whether it be go to another piece of code, or it could even be to write data to a database. Again, I just need to insert some kind of instruction that makes me able to do something on your computer at a different time when some other piece of code is running, and that's how it happens. I know I went off a little bit on a tangent on this one, but it's pretty cool. I definitely recommend to do a little bit of research on buffer overruns. It's a pretty simple way, and it used to be a pretty prolific to do it. And hackers looked for these buffer overrun areas all the time, and found them, and then just was able to really map things out. It was pretty bad. So that's why a lot of the more higher level languages make sure that this doesn't happen. So be careful not to use invalid subscripts. Make sure you're checking if you, especially if you are really using like an array of chars or anything, that could have to where you go past the subscript. Like, for example, if you're asking for input, always check that they haven't given you more data than you wanted them to. Doing so is a great place to create a buffer overrun. Doing so can corrupt other memory locations, cache programs, or lock up computers and cause elusive bugs. By the way, elusive bugs, that might also, I think they should have added this, or allow users to hack your program. This happens all the time and can cause buffer overruns or buffer underruns. Same concept, by the way. Underruns means you're just going the opposite direction. You're pushing memory to the left side of the memory rather than the right. And here is one of the notorious ways you're going to do it, and most likely you're going to do it because we're so used to starting with 1 and counting up. But if you forget to start your counter at 0 and you make it 1 and you go to the size, then you are actually going to go. Everything's going to be off by 1. Including a buffer overrun. All right, so I know that we haven't covered much in this video, but we did talk a lot about that buffer overrun. So I'm going to call it a day on this particular video and let you regroup and come back and see the next section, which is going to start off with the range-based for loop. All right, we'll see you shortly.